Algebraic Structures, Lecture 13, Ring Miscellanea. During the second half of the course, we are going to talk about fields and the corresponding Galois theory. So in order to be able to talk about fields, we have to start with a general recap about the notion of a ring. And in order to define a ring, let us recall what are monoids and groups. So a monoid is a tuple which consists of a set S, an associative binary operation star on this set, and associativity means that A star, the outcome of B star C, should be equal to the outcome of A star B star C for all A, B, and C in S. And an identity element E in S, and the fact that E is an identity element is recorded in the following axiom, that E star A is equal to A star E is equal to A for any A in S. Next, recall that a group is a monoid, G star E, in which each element has an inverse. That is, for any element A in G, there is B in G, such that A star B is equal to B star A and is equal to the identity element E. Here are some basic examples. The set of all non-negative integers with respect to addition and with 0 as the identity element is a monoid. The same set with respect to multiplication and with 1 as the identity element is also a monoid. And the set of all integers with respect to addition and 0 as the identity element is a group. Also recall that a monoid or group is called commutative, alternatively abelian, provided that the operation, the binary operation, which is a part of the structure, is commutative. That is, A star B is equal to B star A for all A and B. Now we can define the notion of a ring. Definition: a unital ring is a tuple which consists of a commutative group R plus and 0, then a monoid R dot and 1, and the two operations on our set R are connected by the distributivity laws, which means that for all A, B, and C in our ring R, the following two identities should hold. First of all, A times B plus C should be equal to A times B plus A times C, and then B plus C times A should be equal to B times A plus C times A. And just like monoids and groups, a ring R is called commutative provided that the multiplication in this ring is commutative. So the addition in any ring is commutative by definition, so the ring itself is commutative if and only if the multiplication is commutative. So for example, integers with respect to the usual addition, multiplication, and with the corresponding identity elements 0 and 1, that's a commutative ring. Moreover, similarly, the set of all rational or real or complex numbers with respect to the usual addition and multiplication and with 0 and 1 as the neutral elements, that's also a ring. Finally, for any commutative ring K, the set of all polynomials with coefficients in K with respect to the usual addition and multiplication of polynomials and with 0 and 1 as the neutral elements, so these are the constant polynomials, that is a commutative ring. The next example is a little bit less trivial. So let K be a commutative ring. For any positive integer n, consider the set mat n times n over K of all n times n matrices with coefficients in K. Let 0n be the zero matrix of size n times n, and let En be the identity matrix of size n times n. Recall that the identity matrix is a diagonal matrix with ones on the diagonal, and all off-diagonal elements are equal to 0. Then the set of all n times n matrices with coefficients with k. With respect to the usual matrix addition, when we add matrices, we just add coefficients component-wise. With respect to the matrix multiplication, that's a complicated procedure given by some strange formula. And with our zero matrix and the identity matrix as identity elements, this is a ring. And this ring is usually not commutative. It is in fact commutative if and only if n is equal to 1. Next, let us talk about ring homomorphisms. Let R1 and R2 be two rings, and just to be precise, we denote the corresponding operations and identity elements with subscript I, where I is 1 or 2, to distinguish R1 from R2. Definition: a map phi from R1 to R2 is called a ring homomorphism, provided that it intertwines all respective structures. So this means the following. First of all, phi maps addition in ring R1 to the addition in ring R2. This means that phi of A plus B, so here plus is in the ring R1, should be equal to phi of A plus phi of B. Now this is plus in R2. And this should hold for any A and B in R1. We have a similar axiom for multiplication. Phi of A times B should be equal to phi of A times phi of B. So on the left-hand side it's multiplication in R1, on the right-hand side it's in R2. Also, phi should map the zero element in R1 to the zero element in R2, and the identity element in R1 to the identity element in R2. So for example, the identity map on any ring is a homomorphism from this ring to itself. Also some remarks: we will usually write R for a ring instead of the full tuple if the structure is clear from the context, so quite often it's uniquely defined. So Z, the set of integers, is a ring with respect to the usual addition and multiplication, and so on. And another remark: we will always assume that in our ring 0 and 1 are different elements. So what happens with the ring where 0 is equal to 1? It's a nice exercise to think about. Next, let us talk about ideals. Let R be a ring. Definition: a subset I of R is called an ideal, provided that I is an additive subgroup and, additionally, it is stable under both left and right multiplication with elements in R. So in particular, this means that R times I belongs to I and I times R belongs to I. Remark: any ideal is automatically not empty because it's an additive subgroup, so it contains 0. For example, the ring R itself is an ideal of R, and the second example, the set 0, just the singleton set consisting just of the 0 element in R, is an ideal of R. That's because if you multiply 0 with any other element, we will get 0. Example 3, let R be a commutative ring. Then for any element A in R, we can consider the set A in brackets, that's the set A times R, so the set of all elements in R which are divisible by A. This is an ideal of R called the principal ideal generated by A. So you need distributivity to show that this is an additive subgroup, and then the fact that it's stable under multiplication with R is obvious from the definition. Now we can talk about quotients. So let R be a ring and I an ideal of R. So this is usually denoted similarly to the notion of a normal subgroup in a group. Then the set of all cosets of R modulo I as an abelian group. So R is an abelian group, I is a normal subgroup. It's a subgroup, so it's normal because the group is abelian. So we can consider the corresponding cosets, and the set of all these cosets, the claim is that this set has the natural structure of a ring, in which we need to define multiplication, and the multiplication is given by defining it using representatives. So the class A plus I times the class B plus I is by definition the class A times B plus I. And the unit element in this ring is the coset which contains 1, so it's 1 plus I. In order to check that this is well defined, so let's take A prime and B prime, the elements such that A prime belongs to A plus I and B prime belongs to B plus I. So A prime is equal to A plus X for some X in I, and B prime is equal to B plus Y for some Y in I. Then the product of A prime and B prime, which is equal to A plus X times B plus Y. This is equal, if we open the brackets, which is allowed due to distributivity, we will get AB plus, and then AY plus XB plus XY. But since I is an ideal, this whole sum belongs to I, so that's an element in AB plus I. So this proves that our multiplication is well defined, and then all axioms of a ring are obviously satisfied. So this quotient, R modulo I, is called the quotient of R modulo I. Now we can just take the usual notions of kernel and image from the group theory and define it in the theory of rings. So let phi be a ring homomorphism from a ring R to a ring Q. Then the kernel of phi, that's the kernel in the usual sense of group theory. R is an additive group, so kernel is the set of all elements in R which ascend to the zero element in Q. So this kernel is an ideal of R. Indeed, by definition it's an additive subgroup, and if you take an element A in R and B in the kernel, and if you compute phi of AB, so since phi is a homomorphism, this is equal to phi of A times phi of B, but phi of B is 0 because B is in the kernel, and anything times 0 is 0. So phi of AB is equal to 0, which means that AB belongs to the kernel. So this means that kernel is stable under the left multiplication with elements in R, and the same argument shows, of course, that it is stable under the right multiplication. So the kernel of any homomorphism is an ideal in R, and the image of any homomorphism is, of course, a subring in the target ring Q, and just if we take the first isomorphism theorem from the group theory, we will get that the quotient of the original ring R modulo the kernel of phi is isomorphic to the image of phi. So we have the first isomorphism theorem in the context of rings. Next, let us talk about various types of special elements in a ring. And we start with zero divisors. Let R be a ring. An element little r in R is called the left zero divisor if there is a non-zero element A in R such that R times A is equal to 0. Respectively, little r is a right zero divisor if there is an A such that A times R is equal to 0. So for example, the zero element is both the left and the right zero divisor because 0 times anything on any side is 0. Example 2. Consider the ring Z sub n, which is a quotient of the ring Z modulo the ideal consisting of all integers divisible by n. Then an element k, so the class of k in this ring, is a zero divisor if and only if the greatest common divisor of k and n is not equal to 1. So if and only if k and n are not coprime. Indeed, if the greatest common divisor of k and n is equal to 1, then there are integers a and b such that we can write 1 as ka plus nb. We can always write the greatest common divisor as a linear combination of the elements. In this case, of course, the class of k times the class of n is equal to 1 plus something which is divisible by n. So divisible by n means 0 in Zn, so it's equal to 1. So this means that in this case, our element k is invertible. And so, if we write k times something u is equal to 0, then our class of u, which is of course equal to u times 1, and we can write 1 as k times a here, and now this is equal to 0 times a, because k times u is 0, and this is equal to 0. So if we take an invertible element and we multiply it with something such that the outcome is 0, this something already should be 0. So this means that in this case k is not a zero divisor. On the other hand, If the greatest common divisor of k and n is greater than 1, then of course n divides the product of k with n divided by the greatest common divisor. And this means exactly that the class of k times the class of this non-zero element n divided by the greatest common divisor is equal to 0 in Zn. So in this case, k is indeed a zero divisor. Now we can talk about domains. Let us remark that if A is an element of ring R, and it is a non-zero left zero divisor, then by definition A times B is equal to 0 for some non-zero B. And then this B is a non-zero right zero divisor. So existence of non-zero left zero divisors implies existence of non-zero right zero divisors, and vice versa. Therefore, we can make the following definition. A ring that does not have any non-zero zero divisors, regardless from which side, because their existence is equivalent, is called a domain. And a small remark, a commutative domain is often called an integral domain. For example, Z is an integral domain. It's a domain and it's a commutative ring. Example 2, as we have seen before, Z sub n is a domain if and only if n is a prime. So a zero divisor in Z sub n is an element which is not coprime with n. So such elements exist if and only if n is not a prime number. So Zn is a domain if and only if n is a prime. Also, so if we have a commutative domain R, then the ring of all polynomials over this R is a domain. That's a trivial observation based on the definition of multiplication for polynomials. Now we can talk about prime ideals. Let R be a commutative ring and I an ideal of R. Definition: I is called prime provided that the following holds. For all A and B in R, the fact that the product AB belongs to I implies that either A belongs to I or B belongs to I. For example, an ideal generated by an integer n, which is not 0 and not plus and minus 1, and this is an ideal in the ring of all integers, this ideal is prime if and only if n is a prime number. That's just equivalent to the notion of being a prime number. Another example, if we take a commutative ring R, then this ring is a domain if and only if 0 is a prime ideal. So any ring has an ideal which is just a zero element, and this ideal is prime if and only if this ring is a domain. In fact, this example can be generalized as follows. Proposition: an ideal I of a commutative ring R is prime if and only if the quotient of R modulo I is a domain. Proof: let A and B be two elements in R such that A plus I and B plus I are non-zero elements in R modulo I. So this means exactly that both A and B do not belong to I. If I is prime, then of course the product of A and B doesn't belong to I, and this means that the product of the classes A plus I and B plus I is non-zero in R modulo I, and this means that R modulo I is a domain. A product of two non-zero elements is non-zero. Conversely, if R modulo I is a domain, then the product of A plus I times B plus I should be non-zero, and this means that AB should stay outside I, and this proves exactly that I is a prime ideal. Now let us talk about inverses in rings. So let R be a ring and little r an element in this ring. Definition: an element A in R is called the left or right inverse to this element little r, provided that A times R is equal to the identity for the left inverse, respectively R times A is equal to the identity for the right inverse. Remark: the zero element doesn't have any inverses, that's easy to see. And a little observation: if our ring R is a domain, and little r is an element in R, and A and B are two left inverses of this element little r, then A is equal to B. Indeed, the fact that AR is equal to BR is equal to the identity implies that A minus B times R is 0. And since R is a domain, this means that A minus B is 0. And so A is equal to B. And similarly, we can check this on the other side. A little remark. If some element little r has both a left inverse and a right inverse, then these two necessarily coincide. We saw it for groups. And this common inverse is usually denoted R inverse. And an R, which has both left and right inverse, is usually called invertible. So if you have an invertible element, it has a unique inverse. And now let us compare these two zero divisors and invertible elements in finite commutative rings. Proposition. Let R be a finite commutative ring and A a non-zero element in R. Then A is either invertible or is a zero divisor. So in finite commutative rings, we have a dichotomy that an element is either invertible or is a zero divisor. Proof. Consider the map which takes an element x in R and maps it to the product AX. There are two possibilities for this map. It can be bijective, and if it is bijective, then there is B in R such that AB is equal to 1, and hence A is invertible. On the other hand, it is possible that it's not bijective, and then, if it's not bijective, it's a map from a finite set to itself. Such map is not injective. But this means that there exist B and C in R which are different, so B is different from C, but such that AB is equal to AC. But then A times B minus C is equal to 0, and B minus C is not equal to 0, which means that A is a zero divisor. And this completes the proof of this proposition. Now we can define the notion of a field. Definition: a field is a commutative ring in which each non-zero element is invertible. Example 1. Rational numbers, real numbers, and complex numbers, these are three classical examples of fields. Example 2. The ring Z is not a field. So the ring of all integers, that's not a field because, for example, 2 is not an invertible element. However, Z sub n, so the quotient of Z modulo nz, is a field if and only if n is a prime number. Example 3. If K is any of the fields Q, R, or C, then the set K of X of all rational functions with coefficients in X is a field. Recall that the rational function is an equivalence class of expressions f of x modulo g of x, where f and g are polynomials in X and g is non-zero. And the equivalence is given by the following rule. So f divided by g is equivalent to u divided by v if and only if f times v is equal to u times g. And the addition and multiplication of such expressions are defined using the usual addition and multiplication for fractions. And here, of course, the point is that an element is non-zero if and only if f is non-zero, so g is non-zero by definition, and then the inverse to f divided by g is g divided by f. Therefore, the set of rational functions is a field. Now we can talk about maximal ideals in rings. Let R be a commutative ring. Definition: an ideal I of R is called maximal provided that it is different from R and it has the following property. If J is an ideal of R such that J contains I, then either J is equal to I or J is equal to R. So in other words, a maximal ideal is a maximal element in the partially ordered set of all proper ideals of R, where the partial order is given by inclusions. For example, if R is a field, then 0 is a maximal ideal. Indeed, any non-zero element A in R is invertible, and so if we generate by such an element our ideal, we necessarily will get the identity element, and of course the identity element generates the whole of R. So any ideal generated by any non-zero element is the whole of R, so these conditions are trivially satisfied. And also we can see that an ideal generated by a positive integer n in the ring of integers is maximal if and only if n is a prime number. And here is a connection between maximal ideals and fields. Proposition: let R be a commutative ring and I an ideal in R. Then I is maximal if and only if the quotient of R modulo I is a field. Proof: assume that I is maximal and let A be an element in R which is not in I. Then the ideal generated by I and this A must be equal to R by the maximality of I, because it contains I and is different from I. And therefore we can write identity as A times X plus Y, where X is some element in R and Y is some element in I. But this means exactly that A plus I times X plus I is equal to 1 plus I, and so A plus I is an invertible element in the quotient of R modulo I. And this shows that R modulo I is a field. And all this argument can be now read from bottom to top, so we can invert all steps in this argument and show that if R modulo I is a field, then we deduce that I is a maximal ideal. Finally, let us talk about irreducible elements in commutative rings. So let R be a commutative ring. Definition: a non-zero element A in R is called irreducible, provided that it is not invertible, and for any xy in R, the equality A is equal to xy implies that either x or y is invertible. So an element is irreducible if you cannot decompose it into a product of two non-zero non-invertible elements. For example, a non-zero non-invertible integer is irreducible if and only if it's a prime number. Another example: if you have a polynomial of degree at least 1 with complex coefficients, this polynomial is irreducible if and only if it has degree 1. That's a consequence of the fundamental theory of algebra, that each polynomial with complex coefficients, which is not constant, has a root. Let us remark that polynomials of degree 0 are exactly the invertible elements in the polynomial ring, and that the degree of the zero polynomial is usually not defined. Now we can talk about prime elements. Let R be a commutative ring. Definition: an element P in R is called prime, provided that it is not invertible, and for any x, y in R, the fact that this element P divides x times y implies that it either divides x or it divides y. Again, an example: a non-zero non-invertible integer is prime if and only if it's a prime number. Example 2, a polynomial with complex coefficients of degree at least 1 is prime if and only if it has degree 1. And a little observation: each prime element of a commutative domain is irreducible. Indeed, if P is prime and P is equal to A times B, then P must divide either A or B. So let's say that P divides A. Then we can write A as P times X, so we have P is equal to P times XB, which we can rewrite as P times 1 minus XB is equal to 0. But now, since our ring is a domain, we deduce that 1 minus XB is 0, so 1 is equal to XB, and so B is invertible. So prime elements are irreducible in commutative domains. The inverse is not true in general, but it is true in a special class of rings which are called principal ideal domains. Definition: a commutative domain R is called a principal ideal domain, or a PID for short, provided that any ideal of R is principal, that is, has the form A in brackets, so it's generated by one element in R. So for example, the ring of integers is a PID, any field is a PID, and for any field K, the ring of polynomials in one variable over this field is a principal ideal domain. And if you have a principal ideal domain, then in such a domain, every irreducible element is prime. So in the PID, the notion of an irreducible and a prime element, these two notions coincide. But in general, it's not true that irreducible elements are prime. And our last claim for today, which is one of the main properties of principal ideal domains, is that in principal ideal domains we have unique factorization into irreducible elements. And that's the following theorem. Let R be a principal ideal domain, then any non-zero and non-invertible element of R decomposes into a finite product of irreducible elements. Moreover, if we have two such products, if we can write A as x1, x2, and so on, xk, or alternatively as y1, y2, and so on, yn, where all elements are irreducible, then k necessarily equals m, so the lengths are the same, and there is a permutation sigma in sk, and invertible elements epsilon1, epsilon2, and so on, epsilon k in R, such that xi times epsilon I is equal to y sigma of I, for all I between 1 and k. So we have the unique factorization of any non-invertible non-zero elements of principal ideal domains into a product of irreducible elements. Some problems and questions at the end. Problem question 1. What can one say about a ring in which 0 is equal to 1? Problem question 2. Prove with all details that in any ring R, the product of 0 with any element on any side is 0. Problem question 3. Construct an example of a ring and an element in that ring that has a left inverse but no right inverse. Problem question 4. Prove that a map from a finite set to itself is bijective if and only if it is injective. And problem question 5. Prove that a commutative ring R is a field if and only if R has exactly two ideals, 0 and R. Thank you very much and see you next time.